Right, hello there ladies and gents, welcome to another video. Today we're going to be working on this PlayStation 5. This has been sent in by a business customer because it doesn't turn on. So they've taken it in their repair shop and they can't figure it out, so they've sent it to me. But it doesn't turn on and yeah, that's all we know about it. Hopefully we're going to be able to fix it. But with that being said, my name's Hakko, I'm an electronics technician. I do mainly work on consoles, but I do work on other stuff as well. So if you enjoy that kind of thing and you want to see more, be sure to get subscribed and turn on the bell notifications. That way you won't miss any future videos. If you need to organise a repair, get in touch at thecoder.repair. And if you need parts and supplies to assist with your repair, you can buy those on my online store at consolefix.shop. All the links in the video description, as well as the links to the tools and stuff that I use in these videos. But with that being said, let's get into today's video. So this is no power, so if I try and turn this on, you'll see that it does beep once, but we don't get any lights on the console. And if I wait around about 30 seconds, it will beep again, but again, obviously same thing, no lights on the console, doesn't attempt to turn on, right? So there you go, just like that. So let's have a look. So I'm going to start off with taking the console apart. Once I've taken the console apart, I'll connect it up to something called UART. UART stands for Universal Asynchronous Receiver and Transmitter. And basically, it's just a diagnostic tool that we use for communicating with the PlayStation 5 or any device that supports UART, really. But basically, you got one of these USB TTL devices, and this TTL device, it can do 3.3 or 5 volts. We need it to do 3.3 volts for the PlayStation 5 because that's what the PlayStation 5 supports. So I've only got 3 wires off this. I've got ground, TX, which is the transmit line, and RX, which is the receive line. And I'll show you where on the console, when I get inside it, where it needs to connect to in order to communicate with the system. So I'll fast forward through this bit and I'll pick the video up when I'm ready to work on it. Some of the screws have been left pretty loose there. It's not a great start. But yeah, I'll skip through the boring bit. Right, okay, so I have the motherboard fully stripped down now. I've just got to disconnect the ribbon cables. That sticker's been ripped off, so that's always nice. It's going to peel off as soon as I try and use the pull tab on it. But never mind. We've got a couple of screws missing in the board itself. That's fine, that's not a problem. I can replace those if needed. But there are 2 screws missing. But yeah, I've got the board itself out. So what I'm going to do is I'm going to pop under the microscope and just show you where we need to connect to in order to communicate through UART. Alright, so if we look on the board here, it looks like this has already been UARTed by someone else. I'm not sure what's going on with those solder joints, but they're not great. But yeah, that's fine anyway, it doesn't really matter because we are going to be cleaning it all up anyway. But really, the flux should have been left. The flux should have been removed from the board. Okay, so first of all, we've got a ground point right here. So this part here is going to go to ground. That's going to be my green wire. There we are. I'll move that out of the way. And then my orange wire, if we look on my UART here, my orange wire goes to RX on the TTL device. That's going to go to TX on the board. Just there. And then my yellow wire is TX on the TTL device. That's going to go to RX on the board. So if you've been following along, you'll know that we have to flip the cables around because we want to send from one device and receive on the other. And we want to receive on that device and send from the other. Hopefully that makes sense. Not sure what kind of flux that is, but it doesn't look great. Okay, so I've got myself a PS5 power supply here. This is the 1200 series supply. So it's the correct power supply for this board. This is one of my own power supplies. I know that the power supply isn't going to be the cause of this because it does attempt to turn on. We don't see any lights or anything. If it was the power supply, it would either not turn on at all or we would get what's known as a 2-second blue light of death, where the blue light will come on for 2 seconds and then shut back off. But that's really not a thing these days with the PlayStation 5, because we don't have separate 5 volt and 12 volt supplies on the power supply itself. So it's really not a thing on the PlayStation 5 for that reason. We used to get the 2-second blue light of death when we'd have 5 volts on the power supply but not 12 volts. If I just plug that in there, and then what I'll do next is just connect up the UART reader, the TTL device, to the PC. So I'll just plug that in there, and then if we head over to my desktop, what I've got here is my UART-CL. This is the command line version of my UART reader tool. So I created this completely free. It's available on GitHub. You can download it for free. You can use it for free, whether you're an individual or a business, doesn't matter. But if we just select option 1, I'm going to select the COM port which corresponds to my TTL device. I know that's COM13, it's always COM13, but you may need to check in Device Manager to see which one is yours. So if we just select option 2, we get a F7001 error and potentially an SSD controller error. So if we look here, we've got possible 504X 2 volt. Okay. So 504X, I believe that's a MOSFET, but the question is, do we actually get 2 volts on this when we try and turn the console on? Alright, so I'm just going to unplug that. Really not sure what type of solder was used on this, but it certainly wasn't leaded. Funnily enough, you can buy leaded solder from consolefix.shop, genuine Kester. Alright, anyway, enough shilling. Let's get rid of this flux that was left on the board. So a bit of isopropyl. That will do for now. Okay, so first thing I'm going to do is hunt around the board under the microscope for any shorts on common areas or in common areas. So it does say to check F7002. F7002 on this is on the other side of the board, but this is also a 5 volt to 1.8 volt area. So let's just have a look on here first because we're in this area. So I've got my multimeter set up in continuity mode. I'm just going to check for any shorts. Oh, I've just gone straight to the source of the short. You have to be kidding me. Wow, that was quick. I swear I have not looked at this board before now. Okay, so we have a short here on this 5 volt to 1.8 volt rail. So this is actually the 1.8 volt side, which appears to be short. Yeah, okay. So this cap here is a 5 volt cap, or rather it's connected to a 5 volt rail. This circuit is very, very confusing in the way it's laid out. So if we look really close, you'll see that the pads for the 5 volt cap, or well, I'm going to call it a 5 volt cap, but basically the pad for this cap here, this 5 volt line here, isn't actually connected to here. This inductor here goes to this pin here. So this is a 5 volt pin, pin number 2 on the right. I don't know what pin that actually is. I think it's pin number 6 or 7, I don't know. And then 6 or 7 on this side. I don't know which way the pins go. It might be, I think this is pin 6 and this is pin 7. I think it goes 1, 2, 3, 4, 5, 6, 7, 8. So the 1.8 volt line comes out of this pin here, this bottom right pin. Well, 2 from the bottom. Hopefully you understand what I mean there. You can see it goes straight into there though. I believe the bottom pin is probably ground. Is it? I don't know. I can't get a probe in there, it's too thin. But yeah, this line here anyway isn't connected to this line here. So as you'll see there's no beep. But this line here is actually shorted to ground. So we have a short on 1.8 volt, which is why we're getting an F7002 error code. Because if we look on the other side of the board, you'll see here, this is F7002, right? So let's check this fuse. Is this fuse blown? It might be. In fact, no, it probably won't be because it's not a 5 volt short, it's a 1.8 volt short. So no, that fuse is not blown and it's not short. And also the inductor for the 1.8 volt isn't short on this side either. So we do have what appears to be a short on the other side. So is this short going to be because of the Wi-Fi chip, maybe? It's possible. Let's have a look. So I've got one probe on ground, so that'll beep. That won't. Oh. That's a 1 ohm short. That is reading as 1 ohm on this cap here. So the chances are either the Wi-Fi chip is bad or one of these caps on the Wi-Fi circuit is bad. That's showing a short as well. That shouldn't show a short. And it's that same 1 ohm short. Yeah, and that one. It's the same 1 ohm short. Now, the thing that you might suggest, you might think is, oh, it's got to be the Wi-Fi chip because multiple caps on this line are short. Well, not necessarily. All of these lines are all connected together, and for that reason, if one of those caps is short, then we're going to end up with all of them being short because they're all connected together, right? So the best thing to do here is my favourite trick: inject voltage. So I'm going to inject voltage. I'm going to use my new thermal camera here. This thermal camera is great. It should pinpoint the issue. Now, this is a 1.8 volt line, so we can't inject more than 1.8 volts into it. However, I'm going to start off. Damn, that scared me. My email just went off and it scared the living crap out of me. I'm going to be using the P3 thermal camera. I am not sponsored by this company, but they did send this for free, and it is, excuse me, an absolutely fantastic thermal camera. But I'm going to be using this just to see if we can isolate this short. So I'm going to connect this up to my type C and then connect that up to type A. One downfall for this is I can't seem to get it working on type C, but that could just be my motherboard. I'm not 100% sure. But what I'm going to do is I'm going to take my probes here and I'm going to connect up to my bench power supply. I'm going to be very careful here because right now I'm connected up to a 24 volt source, and this is going to be up to 10 amps of current, which is very, very bad for the board. So I'm going to make sure I change that. So I'm going to go down to 1 volt. Okay, so I've got 1 volt here. Let me just make 100% sure because of the way my bench power supply is set up at the minute. Yep, 0.99 volt, good, okay. Look how accurate that multimeter is. I've got it set to 1 volt, and we get 0.998. Nice. Alright, so I've got 1 volt connected. And the reason I'm going to go for 1 volt is because this is a 1 ohm short, so it's almost directly short to ground, right? So we shouldn't need too much power, too much voltage, in order to get a decent amount of current going through this. So I'm going to load up my thermal camera. So this thermal camera does work on the PC. So I'll just connect that up there. There we are. Right. Okay, so the good thing about this thermal camera, the one thing I do like about this is that it does allow me to adjust the focus so as I can see the board nice and clearly. Okay, so I'm going to inject 1 volt into the inductor which was short, just to see if I can see the short with the thermal cam. So I'll move that probe out of the way. And injecting. We get 400 milliamps of current. And I am starting to see a hotspot on the Wi-Fi chip itself. So that is getting a little bit warm. I can see a little bit of a change in colour there. Obviously, the probe is getting warm because we are directly short to ground. But I am going to go for a little bit more here. I'm going to go up to 1.5 volts just to give me a little bit more juice. Okay, and we get 700 milliamps of current now. And it is washed out, but it is starting to get warm on the Wi-Fi chip itself. Right, so I'm focused directly on the Wi-Fi area here. And if I inject again, that was a bit of a spark then. Kind of strange. Okay, we are getting hotspots on everything around there, which means it's very, very likely going to be the chip itself. Yeah, the heat is definitely coming from this side of the board. 100% on that. So it's coming from this side of the board, and it looks like it's coming from the Wi-Fi chip. Okay, good. So we are being covered by the shield, but it looks like the Wi-Fi chip is definitely at fault there. So I'm going to remove the Wi-Fi chip then. So I'm going to start off by just moving the heat around a little bit, just get some heat in the board. Okay, so that's pretty much ready to remove. So if I just slide this over to the edge, I can then grab it. There we are. And that's removed. Right, good. So if I go back to this 1.8 volt line here, if I just pop one probe on ground and the other probe on the inductor. Oh, sorry, I'm not even in continuity mode there. Bear with me. Now I am. Okay, so one probe on ground, other probe on the inductor, and bang, the short is gone. Good. That's awesome. Yep, good stuff. Right, so we definitely have a short on the Wi-Fi chip. That chip is definitely bad. The problem is we can't buy the little chip that's inside here. So this is just a shield, and the bottom of this is basically just a PCB, right? It's just a module. There's a chip inside along with a bunch of components, a bunch of capacitors and resistors and filters and stuff like that, right? The problem is we can't buy the actual chip, or at least last time I looked we couldn't buy just the chip to fix the Wi-Fi module. The easiest thing to do in this situation is just to change the chip, or change the entire module rather. So I'm going to grab one from a donor board. So this one here is a J20H100, but it is compatible. And the way I'm going to remove this one in particular is if I bring my board over to if I bring my microscope over to the edge of the table, so you can see the edge of my table there. If I just heat up from underneath the board, we'll be able to remove this safely without risking any damage to it. So that's what I'm going to do. I'm going to take my hot air and heat up directly underneath. So you can see my hot air one there. I'm at 440 degrees Celsius, 40% airflow. And in fact, I'm going to go to 480 at 60% airflow. I'm going to do exactly the same thing. I'm just going to slide this off. So there's no real sensitive components here which I care about. There are some, coax connectors, but I don't care about those. All I care about is just removing this as safe as possible. And it's a bit more difficult at 440 when you're doing it from underneath the board. As you'll see there, that's already done. It's already ready. If I lift that off, there's my donor chip. So, as you can see underneath here, this is just a BGA PCB. So it's basically a PCB with BGA pads on it. And obviously, to be able to use this chip, we need to replace the solder balls that were on there with some fresh leaded solder balls. It can be lead free, but I use leaded. I'll grab a bit of flux like that, and then what I'm going to do is I'm going to take some leaded solder and just replace the solder that's on these pads with some leaded solder. That's just going to lower the melting temperature and make it easier for me to wick the pads away. So I'll just flood that with solder. There we are. Beautiful. Excellente. Good. No, not good. We have a missing pad on this. Ugh. I'm not wasting a chip. I'll do a trace repair first. That's annoying. How do we have a missing pad on there? Alright, whatever. Let's grind the wire away. Okay. And I'll tin the wire, and then I'm just going to wick away the solder from off the actual chip. So if this was one that I was reselling, I would never add a jumper wire to it, but I do know that I'll be able to solder this on and keep that jumper wire in place, so it's fine. It's pointless wasting a chip just because we've got a missing pad. I don't know how we've got a missing pad because I removed that fairly safely. It might have been weakened. Alright. So before I get rid of the flux on here, I'm going to add a jumper wire to this pad here. A bit of a reflection on there at the minute, but I'll sort that in a second. So what I'm going to do is just tin a bunch of this enamel wire that I've got here. And then I'm going to add that wire there. You can't actually see that because I suck at doing this. YouTube, I mean. Alright, I've got that in position there. I've just popped a bit of solder onto my iron tip. And there we are. Okay, so I'm going to press down on the jumper wire here now. Just make sure it gets flowed into place properly. Good. Just snip that off there like that. And then before I actually position this, I'm just going to clean the chip. A bit more IPA there. Alright, good stuff. So let's clean the IPA from around my desk and then also from off the chip as well. Good. That looks pretty good to me. So what I'm doing here essentially is I'm going to create a new pad. So we need to curl up this wire. So we get that into position like that. There we are. And then what we need to do after that is protect this so as we can use heat on it without it falling off, right? So I've got myself some Relife RL UVH902. This stuff is absolutely fantastic. I'm just going to use a smidgen of this stuff. Basically this is a UV mask or UV glue. It cures with UV light. And I'm just going to coat the area with a little bit of this. Just a smidgen. There we are. I could probably do with a touch more over here. We don't want to cover the other pad. But there we are, that's that done. And then I'm going to take a UV light for 3 seconds. And that's cured. There we are, look. We can make it go a little bit harder. Just by curing it for a few more seconds. But we're good to go there. So the problem we've obviously got now is this is uneven compared to the rest of it. So I'm going to grind it away a little bit. But I also need to expose the pad anyway. Just clear that away and then we should have an exposed pad. Good. Let's just check in diode mode, see if we get a connection. I don't know off the top of my head which pad is ground. However, I can just, or should just be able to connect straight to the shield, which is what I'm going to try. Let's just see if I get a diode reading there. I do. I'll get a 0.32 volt diode reading, which is about right, I would say. So we do have a contact on that. That's good. And now I should just be able to reball this as normal. So what I do with these BGA chips, or these Wi-Fi chips in particular, is I use a few solder balls on each pad, right? So basically I'm going to be adding 2 balls to each pad, but what I do need to do is just have a look first and just see what I'm dealing with in terms of this jumper wire. So I'll take some flux and I'm just going to spread this flux evenly. We don't want too much in one spot. Just a nice even coat of flux. There we are. And I've got some 0.5 millimeter balls. And I'm just going to drop a couple on the surrounding pads first. So I've got those just off to the side here, as you'll see there. So all I'm going to do is just drop a few of these solder balls on each of the surrounding pads, just so I can flow those ones down, just so I can see what I'm dealing with in terms of how even it's going to be when I do put solder balls on that jumper wire, right? Well, that's the plan at least. So I'm going to go for 2 balls per pad. And you know what? I'm going to go for 3 per pad, I think. And that'll make up a 1.5 millimeter ball on each pad. To start with, I'm going to put 2 balls on this pad and just see how that looks. In fact, I'm going to do these other 3 pads next to it, just so as I've got a nice even amount. So if I do these pads here, it means I haven't got to come back to this side of the chip. I've basically done one corner, right? Okay, so let's flow these down. I'm going to be using 440 degrees Celsius at 10% airflow. I've got a feeling I'm going to be flat enough to the point where I can just drop 3 balls on there though. Yeah, he's definitely going to need another ball. Alright, yeah, so I would say once I add some flux here and flatten these down with a reflow, it should be okay. So it looks like I've got it fairly flat to start with. It's a little bit off. Let's see if I can just dab it with the iron. Just catch a little bit of it. Let's check that. Oh, that's a lot better. It's so much closer. I would say that's probably okay. It's a lot closer than it was, that's for certain. Alright, yeah, I'm going to try that. I'm going to try doing it like that. Right, so I need to just spread this flux out now, just so as I've got flux on the other area, which isn't, you know, minimal sort of thing. So I'll just go like that. There we are. And that should be okay. Right, so let's just drop a bunch of solder balls all around then now. That's more than enough. Okay, and I'll continue to reball the rest of this then. Okie dokie, so I've just about got that reballed. Not many solder balls are left over. Happy days. So I'm going to flow this down. I'm going to go for 10% again, as I did just before. So I'm just going to flow all of these solder balls into place. And we should end up with some beautifully shiny balls. Once they all merge as they should. Just give that one a bit of assistance. There we are. Good stuff. Time for some more flux now. Once it cools down a little bit. You don't want to put flux on while it's actually cooling down, because it can cause the solder balls to deform. You don't want that. Alright. Got one solder ball here in need of assistance. There we are. And now that should be all nice and even. Good stuff. Happy days. Okay, so I'm going to bring this board back into play here. And I need to do the same thing as what I did on the chip with the solder. Just remove all of the solder from the board. But I need to add some leaded solder first, just to lower the melting temperature. Let's wait for that to beep. There we go. Alright, just clean off my iron. And then before I actually do anything else, I'm just going to run the iron across again. Just to gather up a little bit of the solder that's on there. Just reduces the amount of wick I need to use. There we are. So you can see we've got a bunch of solder on the iron. And now I can wick it away. Okay. Good stuff. Right. Ready for the new chip. So it's very difficult to actually get this rung. We do have an indicator up here, top left. And there's also an indicator on the chip. But if you're completely unsure, just look at the bottom. We've got one pad missing there, and we've got a pad missing on the board there. So all we've got to do is just line it up, you see. Just line it up. Get that in position. We do have some guides on there, but if you don't have guides, press down on the chip with 2 fingers, give it a wiggle, and if it's in position, it won't move. If it's even slightly out of position, you see that move then as I wiggled it? If it's even slightly out of position, it will move, but just give it a little bit of a wiggle if you're unsure. Of course, now my finger's stuck to it. Well, you don't have to be dead on, just get it fairly close. Okay, so board over the edge of the desk again, and I'm going to do exactly what I did before to remove this chip from the other board. Heat up from underneath. So I'm going to go 480 at 40% airflow. Sorry, 60% airflow. It's not exactly in line as you'll see there, but surface tension will take over. Just give it a few minutes. Well, a minute or so. And it should be jumping into place in a moment. And just like magic, come on. There we are. It's starting to move now. You'll see it sit down. I'll just move my hot air around a little bit, being careful not to crash into the board. Give the chip a nudge, and now I know it's connected. And hopefully we've got a contact on that trace that I've damaged. I don't know how I did it, but, well, I did it. So, what can you do? So, that's all got to cool down. So I'm going to wait for that to do. I'm going to wait for it to cool down. While I'm waiting for it to cool down, I'm just going to sort out the liquid metal. So I'm going to get a couple of cotton swabs here. And some IPA. And just readjust the liquid metal. By the way, if you want to buy liquid metal, you can buy it from me. Half the price of Conductonaut. If you take into consideration, you get double the amount with me. So Conductonaut, you pay, I think it's about £13 for 1 gram. With me, you pay £12 for 2 grams. Or 12 or £13, can't remember, but it's on the store anyway, check it out. Okay. So give that a clean. And then we're going to move the liquid metal back over. There we go. Perfect. Good stuff. Okay, so I need to clean up this area here now it's cooled down a bit. And then what I like to do is just get my microfiber cloth and make it as good as new. Good stuff. And that is nice and clean. A little bit of discoloration where the flux has been, but you can't help that. Alright, let's give it a test. I just need to fix the liquid metal on the heatsink as well. Just group it all up into a ball. So there's IPA on my cotton swab, and that's why it groups up nicely. Give it a nice scrub. Make sure everything's nice and clean. And then we're going to get a fresh swab and scrub it fully. Scrub it till it squeaks. Good stuff. Right, let's give it a test, shall we? Does it turn on? That's the most important thing. I certainly hope so. Oh, something's just popped. Something's just gone kaboom and that let out some magic smoke. That's not good. I don't know if that come across on camera, but as soon as I plug that in, it's gone kaboom. What popped? I've got a feeling it's this here. As in this voltage regulator. So I saw some smoke come from this. And this 5-volt rail is missing. I believe it's probably short. Let's have a look. So, continuity mode. 1.8 volt short. 5 volt short. So now we've got a short between 5 volt and 1.8 volt, right? So, chances are here that the chip has gone. So it's probably on its way out and it's just gone poof when we've applied power to it. So remove that. And let's check again. No short on 5 volt. But we do have a short on the 1.8 volt again. Why? So 5 volt is now fine, but 1.8 volt isn't. So that's ground. That's 5 volt. That's 1.8 volt. And 1.8 volt is short. Is it that cap? Has that cap gone kaboom? So we definitely have a short on this chip, so I can get rid of that. Ping. Let's leave that there a second. Still short on that side. It's not the cap. Alright, it's voltage injection time again. No, it's the Wi-Fi chip again. It's blowing it. Damn. Okay, so yeah, I know exactly how this has failed and why. So let me explain exactly what's happened here. I'll pop under the microscope and show you. So we've got the 5 volt to 1.8 volt circuit here. What's happened is the chip, the 1.8 volt regulator, has basically failed. It sent 5 volts directly from the 5 volt input straight through to the 1.8 volt. So the 1.8 volt line has received 5 volts. That's blown the chip. And obviously, because I didn't know that that was short to the 5 volt line before, which is completely my fault, it's caused it to blow the chip again. So now I'm down a chip. I can't charge a customer for it because, well, it's not their fault, is it? Never mind. I'll grab another chip. This is just one that I've got on my desk, but should be okay. It's one that I'll have taken off a donor board and just not had a chance to reball. So I'm going to have to reball this quickly. Something I should have checked really. I should have made sure there was no short between 5 and 1.8. Somehow got thermal paste on this chip as well. That's why you shouldn't keep chips on your desk. Let's use some 3.5mm goot wick for this because, well, quite frankly, it's better than the MG chemical stuff. Okay, so yeah, I'm going to fast forward through this, but I'm basically going to be doing the same thing that I've already done. That's going to be reballing of the chip and then prep the board for that new chip. Okay, ready to rumble. Right, where's my third ball? Gone off this one up here. Okay, good to go there. I don't really need to reflow it because the flux will do that when it's on the board. So we're good to go on that one. Okay, did that. pad hold up? Yes, it did, as you can see there. Obviously that chip is now dead though. Right, so because this is ready to solder, I can just run the iron across. Just gather up a little bit of that solder. There we are. Get some solder braid. As you can see, Gootwick is so much better than MG Chemicals. It's a lot thicker and it gathers up a lot more solder. Need a bit of hot air just to assist with this because there's a little bit of a solder blob on the ground plane. There we are. Okay, I've got OPA on my cloth here. Just clean that up. And I've got flux already on the chip. So there's that. And in fact, no, I haven't got flux on the chip. Let's add a little bit. There we are. Just to make my life easier, I'm just going to flow this down from the top of the board. It's not going to hurt it. Might singe the shield a little bit, but it'll be fine. So there's that, sitting down nicely. There we go. Right, we need to fix this area here now. So I'm going to add a touch of flux. Just in those pads. And then I'll grab myself a donor board and grab this chip from a donor. Alright, so first of all, damn it, I was trying to push that capacitor down, didn't work out to plan. I was trying to rotate it so as it would sit back on its pad. I've turned my airflow down now though. Okay, so I'll just add a little bit of flux here, just a little tad. Okay, the chip's dancing, which means it's in position. Not always, but it's in position. Don't worry. Time for a clean up. Alright, good. So, before I go any further, I'm going to check everything. So I'm going to check to make sure we don't have any shorts to ground. And also, I'm going to check my fuses as well. So, first step, 5 volt, no short. 1.8 volt. Why is that short again? How is that short again? What on earth is going on again? How is that possibly short again? It makes no sense. That makes absolutely no sense. Remove the inductor. Isolate the circuit. No short. Short. How is it short again? It's short on this side now. And my 5 volt fuse has blown. Of course it has. Oh, this is annoying. Let's isolate the circuit on this side. Okay, so it's on the output side of the inductor. Oh, this is annoying. So I've got 1.8 volts at up to 10 amps of current here, which I can use. That is drawing the full 10 amps of current. Wow. The full 10 amps of current is being drawn right now, and I'm not seeing any heat spots at 1.8 volts. Apart from on the probes themselves. Whatever the hell he's shorted, he's taking that like an absolute champ. It is not the cap. No way is it the cap. What on earth is causing this short? Wow, those probes are hot as well. Damn. Right. This side. What's going on? What on earth could possibly be taking that much current and not showing up with heat spot? What the fuck? Ow. Oh, that's burnt my hand. Pretty bad. Okay, that was an adventure. So I've had to take a little break because, well, that burnt my hand, as you can probably imagine. Yeah, bit of cold water, my hand's fine. I'm fine. But, yeah, I didn't even realise there was any IPA on the desk. Not good. Not good at all. Right. Is the desk dry? Yeah. It's melted the fuck out of my UART. So that's nice. Like, that was on fire, like properly on fire. And I don't have a fire extinguisher in here. And even if I did, I wouldn't really be able to use it around all of this equipment, would I? But maybe get a fire blanket. I don't know. Yeah, I can't figure out what is actually sinking 10 amps of current. It don't make any sense. The only thing I can think of is a tiny little cap underneath this shield or something is blown and that's causing it, but I don't know. I'm going to remove this Wi-Fi chip because I need to figure this out. I don't want this to beat me, especially with what I've just had to go through to try and actually get this thing working. So I've got my hot air at 440. So just while I'm removing this, I can explain why that fire ignited. There was IPA on my desk, and as I've removed the probes for the bent power supply, that's caused a stray spark. All it takes is one, guys, so just be freaking careful. Just be really, really freaking careful. There's no IPA on my desk now, I've just checked, so we are safe to continue. And yes, sure, I could edit that out of the video. Not going to. Not going to. Why? Because it just shows what can happen, right? It just shows that this job isn't as safe as people believe it to be. Oh dear, right. Let's have a look. What's going on with this 1.8 volt line now? Is it still taking 10 amps of current? No. Yes. It's still sinking 10 amps of current. How? Right, well, this was a complete and utter failure. I nearly burnt down my workshop. I nearly caused first degree burns on my hand. And I've wasted 3.5 hours of my life. Literally 3 hours and 25 minutes. I'm going to go and cry in a corner. Yeah. It's so... Oh, it does beep after a little while. Yeah, nice, thank you. Yeah, it sucks, but it is what it is. I'm going to call it quits. I can't keep working on this. 3.5 hours is far too much. And now I've got a headache. So, yeah, thank you for watching, everyone. Let me know what you think down in the comments down below. What the hell happened? I don't know. But, yeah, that's going to be it for now. I'm sorry, it was a waste of time. Take care, everyone. See you all later. Bye for now.